Greetings, ladies and gentlemen. Welcome to the second public lecture on its association with the Summer School on Galaxies and Cosmology. Thank you very much for coming to this lecture, and we are very happy to share with you lots of new ideas, lots of the enthusiasm of young students who have been with us in the last 2 weeks. With solid theoretical framework and observational evidence, modern cosmology has advanced significantly in the past few decades that we now have quite a confident narrative on how the universe works and evolves on a large scale. Theoretical knowledge constrained by observations both on electromagnetic and gravitational radiations has matured enough to take up the hard challenges. That is the physics of the very early universe. In this lecture, we will learn how we use our knowledge of the present universe to ask how it was in its infancy. The lecturer today, Professor Eiichiro Komatsu, is currently the director of the Department of Physical Cosmology of the Max Planck Institute for Astrophysics in Germany. And he is the world-leading scientist in cosmic microwave background physics. He received various prestigious acknowledgements, including the 2018 Breakthrough Prize for Fundamental Physics for his work with the WMAP, which provided the values of cosmological parameters with unprecedented accuracy, which in turn led to new understanding and quest of the universe. Eiichiro and I met the first time, I think, in 1998 in the Astronomical Institute of the Tohoku University in Japan. It's quite some time ago now, but it was the time when lots of exciting things going on in cosmology. For me particularly, was the time when gravitational lensing was securing itself as a reliable cosmological tool, and the CMB folks were highly anticipating the MAP anisotropy probe of the cosmic microwave background, which subsequently launched in 2001 and added the name Wilkinson onto it. And Professor Komatsu was one of the significant figures who made it very successful. So we are very privileged today to have Professor Komatsu with us, who's really been a part of this WMAP hugely successful mission. So without much further ado, please welcome Professor Eiichiro Komatsu. Komatsu-san, all yours.
Yeah, thank you very much. Hello, everybody. Thanks for joining. I'm very glad to have this opportunity to present my lecture today to all of you. And thanks in particular, Professor Primordial, for the kind invitation. It's always very nice to hear from all the friends. And you know, you meet somebody in the college, university, many years later, and we all become faculty somewhere, then we invite each other. That's how it works. So remember that. It's very nice. I'm really thrilled to be here. So let me try to share my screen. And there you go. Do you? Yeah.
It appears all right. Thank you.
Good. Yeah. And then full screen.
To go.
Yeah. Hold on. Yeah, I know what to do. Yeah, there you go. Okay. So as Professor Premadi said, today's topic is the early universe. And in particular, how we would use gravitational radiation, gravitational wave to learn about the early universe. And the tool that we're going to use is actually not the kind of direct experiments to measure gravitational waves, but the cosmic microwave background. And here you see the Milky Way, and we belong to this galaxy. We are on Earth, and that's inside of our Milky Way. Now, if we wanted to then show the entire sky on a flat screen like this one, we would use so-called galactic coordinates to expand the sky. And then this is the entire sky. Now we go to longer wavelength, visible, infrared, far infrared, so millimeter. By the time you go to microwave, that's about millimeter to centimeter wave, the entire sky is filled with 2.7 Kelvin background photons. That's called cosmic microwave background. That's the ancient, the most distant light that we can observe today. But then you improve your detector sensitivity by factor of 100,000, you will start seeing these ripples. You start seeing places where temperature is slightly lower, places where the temperature is slightly higher. So these are the inhomogeneity in the matter and radiation that existed in a very, very early universe. So it looks like this. So you have, this
Eiichiro,
is.
sorry to interrupt.
Yeah.
Are you on your full screen mode?
I'm sharing the window. Oh, does this change when I change this thing?
Yeah.
I see. So then maybe I should indeed go to the full screen. Hold on. Is this better?
Yeah. Excellent.
Good,
Thank you.
Good. Then let me just try to have the annotation. Yeah, always a challenging thing to just a little bit, just wait a little bit more. Okay, how do
Would you rather the previous setup? That's all right too, except that it's not full screen.
No, full screen would be better. So let me do that way.
Okay.
Yeah. I just wanted to show the annotation, but somehow it doesn't work. Just quickly I go outside of the presentation. Oh, but this is probably okay. Okay, all right. Now, so we have the WMAP satellite here on the right. And then what's shown here is a light cone. As you go to the left, it's more distant place, but also it's in the past.
Now we lost your presentation though, sorry.
Okay. All right. Yeah. Sorry.
Don't worry.
No,
I think it's the.
It's very interesting. I've done this many times, but somehow today is not so good day. All right, but let me then. So you can see the cursor.
Right.
Yeah, and then if I go play, hope you can still see the cursor. Okay.
Yeah. Excellent.
Fantastic.
I think that's
very
on
good.
now.
Yeah.
Thank you. Sorry.
No problem. Thanks for letting me know. So here is the WMAP satellite that Professor Premadi introduced to you. Then photons come from the cosmic microwave background, so-called last scattering surface. That's when the photons are last scattered by electrons. Universe is very hot. Then photons will come to us. But as photons go through, universe evolves. That's why universe looks very different here. So it's distant and past, right? That's the key. The farther away you look, the more distant past you can see, right? So that's the light cone. Now, before this time, however, universe was so opaque, hot, dense, and then photons would be scattered by electrons so much that you can't see anything beyond this directly using photons. So then how do we see beyond the surface of last scattering? This will be the subject of today's lecture, and then we use laws of physics. Now, however, it's a fairly complicated thing when we try to explain it in words or equations. So what I'm going to show you now is a movie. Now, this movie is the full dome movie for planetarium. It's created by the movie director Hiromitsu Kosaka in Japan. He's well-known director for creating the full dome movie, and this is the world first movie on the cosmic microwave background. And let me tell you how this movie was created. It's very interesting. So we are all scientists, and we are given the mission to disseminate our discoveries to the public people who pay tax to support us. Public outreach is super important duty for scientists. So we try our best, but we often fail because we were trained scientists, but we're not necessarily trained educator or public outreach officers. So we are struggling, but then we had this interesting workshop in Japan a while ago. So scientists and science communicators meet, not scientists and general public directly one-to-one, but science communicators first. Then we give lectures to the science communicators, such as curators, but then musicians, movie directors, poets, artists, or anybody who loves the universe. The one of the audience was Mr. Kosaka, and he was inspired by cosmic microwave background so much that he decided to create a movie about it. And then since then, the movie was recorded in both English and Japanese. The Japanese version has been shown at many planetariums in Japan. English version was shown at international competitions with significant honors already. And also at a few planetariums and science museums throughout the world. So this was very effective because, first of all, these are the audience that I would never be able to reach myself. And the movie was so well made that it becomes infinitely easier to explain the complicated concepts. And I hope you see that now. So I'm not going to show you, of course, everything, but I will show you only some of it that's relevant to today's lecture. But you have to imagine that you see the, by the way, you can see the trailer. Not all thing is not yet on the internet, but you can see Horizon Beyond the Edge of the Visible Universe. Google it and you find a YouTube trailer. I hope you enjoy it. Now you have to imagine that because it's a full-dome movie, you see the circle. Middle is zenith, it's top of your head. This side is front, that side is back, this and this is the side. So you just have to imagine, use your imagination to recreate three-dimensional full-dome projection. So there you go.
The cosmic background radiation is the wall at the edge of the visible universe.
Oh, by the way, can you hear the sound? Can you hear the sound? I hope.
Yes, we can hear it clearly. Thank you.
We cannot see directly the further past beyond this wall. But these temperature fluctuations may tell us what happened in the further past.
The conditions beyond the wall of the cosmic background radiation could be thought of as a liquid with high temperature and high density. You could say it was like a hot soup. Something happened behind this wall that made waves, which can be seen in the fluctuations in the cosmic background radiation. There must have been a grand sound that shook the universe. We can learn a great deal about the universe if we can extract this cosmic sound. The origin of the sound would be the moment of the birth of the universe.
So what happens here is that when universe was dense and hot and opaque, the photons and atoms couple together by scattering, and they behave like a single fluid, like a hot soup, as you heard. Then density perturbations occur, and they propagate as the sound waves. And you see only the sound waves that appear at the surface of lots of scattering. And what you saw there is there was some kind of initial impact, and come back to that later. That's an initial condition for differential equations. So namely, motion of the cosmic plasma made of photons and atoms and electrons, they obey second order differential equation in time, but then you apply some initial conditions, they let them evolve. Then they create these sound waves because it's a fluid, and that's what we see. Now, All of these in words would be just too complicated to understand. But with a movie like this one, you immediately get it, right? You saw that the universe looked like a hot soup. There was an initial impact. That's the initial condition. Something happened in the beginning of the universe. Then you solve the differential equations to move initial condition forward. That was a sound wave you saw, and that's what you observe, right? So I hope that you got it. Now, these sound waves in the fireball universe was predicted in 1970 and finally discovered in 1999 and 2000. And one of the first people who predicted this is Jim Peebles at the Princeton University. And for this beautiful prediction, which then later confirmed, he shared Nobel Prize in Physics in 2019. And you see here is the paper, 1970, and you was Jim Peebles' first graduate student who is currently in Hong Kong. And then now this is the very actually pretty impressive drawing here. How does he look in practice? In reality, he looks like that. Well, you see the drawing was pretty accurate. So this is me, and these are our friends. So we had a conference in India, Goa, in 2011, in winter time, although it looks like summer. And we had lots of fun. Now, I said Jim Peebles was one of the first people to predict sound waves. Indeed, there were Rashid Sunyaev and Yakov Zeldovich in Moscow who made the same prediction in the same year. And now he is actually my colleague now. He's also a director emeritus at the Max Planck Institute of Astrophysics, where I am now. But well before that, in 2003, my advisor, David Spergel, had a party in his house. And then we met there. And I was thrilled because, you know, I've read these papers like a million times. He was my hero, as well as Jim Peebles, and it was a fantastic moment. Then, you know, nobody thought that we would become colleagues in later time. So you never know, you know, how life will end up. So sound waves are predicted in 1970, detected in 1999, 2000. And way we detect this is so-called power spectrum that I'm going to explain now. So you had these temperature fluctuations in the cosmic micro background, which you decompose using Fourier transformation into set of sine and cosine waves, and you plot the amplitude of waves as a function of the wavelength. In this case, it's a wavelength, 1 over wavelength, like a pi over wavelength, called wave number. As you go to the right, it's small scale. As you go to the left, it's larger scales, longer wavelengths on the left, shorter wavelengths on the right. And you see something that looks like the oscillation. So that's a cosmic oscillation. And it's a beautiful example of the success of theoretical physics. And with this, so these are actually amount of atoms you can have in the universe. And depending upon how many atoms you have, the waves patterns change. Shape of the power spectrum changes. And that's how you can determine the composition of the universe. And now here is what the power spectrum really is. If you go to the very left, longer wavelength of the fluctuation is as big as the sky itself. As you go to the right, you can start seeing the more fine structures. And you go to the shortest wavelength. That look like that. But after all, you combine everything, you get the original skyback. So this is really nothing but the Fourier transformation, Fourier analysis. Okay.
We can use
now we can try to use this to measure the composition of the universe. It's like you have a cosmic soup. Now, in this case, it's a Japanese delicacy called the miso soup. It's made of soybeans, and there's a tofu that's also made of soybeans. So you see Japanese really love soybeans. It's like you drop tohus into miso soup, you see ripples created propagating with some sound speed. So these are sound waves, or density waves, longitudinal waves, sound waves, and then you just see how they propagate in the miso soup. If you have too much miso, waves propagate slightly differently from that with much less miso. Well, you put, I don't know, I mean, I'm in Germany now, so maybe you can put potatoes instead of miso, then you get something completely different. So in that way, you can really see the composition. And one of the things, I mean, WMAP has achieved many things, but one of the important outcomes of the WMAP was the definitive evidence for non-baryonic nature of dark matter, because we see essentially in the cosmic micro background, you can measure the amount of stuff, the matter that interacts with photons, and amount of matter that does not interact with photons. You can see the sound waves that's given only by the matter that interacts with photons, but the matter that does not interact also gives you gravitational effects, such as gravitational redshift and blue shifts, which you can also measure by cosmic micro background power spectrum. So in this way, you can have accounts of matter that interacts with photons, the matter does not, and that's everything. You can't have anything else. That's all. And the fact that the matter density you get doesn't agree with the matter of atoms indicates that most of the matter is non-baryonic, and there's no question about it. So, so now you see how this works in practice. Well, graphical, but you see that what the universe is made of, how we actually determined baryon density, matter density, dark matter density, dark energy density, but most importantly, how you should think about solving differential equations, right? So you make some impact and recreate the universe in computer and compare that to the observational data. That's how science progresses, okay? You make predictions theoretically, you compare to the data and learn something new. Okay.
Computer calculation to recreate the state of the universe this sound traveled through. The universe at this time was dense and behaved like liquid, such as a soup. Ingredients of the soup are the same as those in today's universe. Matter that makes stars and galaxies. And dark matter and dark energy exist, even though they cannot be seen directly by our eyes. Galaxies can keep their shapes thanks to dark matter providing gravity. It's thought that the universe's expansion is gradually speeding up due to some dark energy pushing space apart. These are the three main ingredients of the soup. Space expanded with time. Let's give some impact to the beginning of this model. Great. I have a pattern for the cosmic background radiation. The reason that this particular pattern does not match our observations is because the ratio of ingredients in the soup is wrong. Waves do not travel through in a thick soup like they do in a thin soup. I'll use the power spectrum to make the patterns match. I have to adjust the ingredients to make my calculation agree with the data. Incredible! The visible part of the universe, like stars and galaxies, makes only 5%. The universe is dominated by invisible components.
So I hope you're convinced of the power of the movie like this one, because if I had to explain this in words, which I kind of did, you're not gonna be able to make people understand what I'm talking about. But with a movie like this one, I hope it was very clear. So we measure the composition of the universe, and that was one of the maybe one of the most well-known results of the WMAP. But today's lecture is something else, and this is also very important results. So I hope you heard. Let's give some initial impact to this cosmic hot soup, right? That, and then something happened, and then sound waves propagated. That's like solving differential equations, right? Initial condition and what follows. But who gave the initial condition? That's the question. A leading idea was, so let's say, if you imagine, right, you drop tohus into miso soup, and the ripples are created, sound waves propagate. Who dropped the tohus, right? That's essentially the question. A leading idea, 1980s, is that nobody dropped the tohus. Tohus emerged quantum mechanically. So these are quantum tohus, if you like, just emerged from the vacuum. Well, that sounds too much. I mean, how can we believe that? Well, we use observations to try to verify it, and I spent most of my career trying to test the predictions such as this one. But quantum fluctuations are everywhere, ubiquitous, we all know this, but they are always confined in a very small volume. They never become relevant on macroscopic scales. So what's the missing link between small and large scales? A leading idea is that there was this exponential expansion period in a very early universe called cosmic inflation. You have quantum mechanical fluctuations with microscopic wavelengths, very short, but then universe expanded exponentially, stretching these microscopic wavelengths to macroscopic wavelengths. It's like you have the size of the solar system, or size of the atom, let's say, initially, but then in a fraction of a second, because of exponential expansion, size of the atom becomes the size of the solar system. And that's a crazy amount of expansion in a short period of time, called inflation. And well, is that really true? Okay. So what does inflation predict then? If inflation predicts something, we can test it. So inflation predicts the following. Distance between 2 points is stretched as A, and A is so-called scale factor. It depends on time. It monotonically increases with time. Then so-called Hubble expansion rate is defined as the A dot over A. So it's a time derivative of A. If universe was expanding, this would be something 0. But to get a rate of the expansion, you divide the A dot by A itself. So it's a logarithmic derivative of A. And this has a unit of time. Now, H is A dot over A. If you integrate, then you get A, that's integration of H, and put in the exponent. During inflation, universe expands exponentially. This means H would have to be constant. So that solution is this one, right? But inflation must end. So this Hubble expansion rate is roughly constant during inflation, but it must be a slowly decreasing function of time. Otherwise, inflation never ends. So how can we test this? So we use quantum mechanics. Heisenberg's uncertainty principle tells you, this is a slightly different version of the Heisenberg's uncertainty principle. Basically, if you promise to return energy in a shorter period of time, you can borrow more energy, right? And in the early universe, there wasn't much time. So in principle, you could borrow a lot of energy from the vacuum. So energy you can borrow will be inversely proportional to the time you borrow. But Hubble expansion rate has units of 1 over time. So energy you can borrow is proportional to H. And here's the key. So H decreases with time, okay? So energy you can borrow was greater in the past, and energy you can borrow is smaller in the future. But now, the earlier fluctuations, right? They were generated, then they were stretched by expansion more. So today, they subtend bigger angles in the sky. They are longer wavelength. So earlier fluctuations have longer wavelength. And shorter fluctuations, shorter wavelength fluctuations were produced later. And because h has to decrease in time, inflation predicts that amplitude fluctuations on large angular scales is slightly larger than that on small angular scales. And that we can certainly test. But if you look at the power spectrum, it's large on larger scale, maybe in going down, but then it goes up again, goes down again, goes up, goes down, goes down. It doesn't look like, long wavelengths is slightly bigger than the shorter wavelengths. But we know why, because we're not necessarily looking at the initial condition here. This is the result of the evolution of sound waves after the initial condition. But now we know the composition of miso soup. Right? We have how much baryons there is, how much dark matter, how much dark energy. So we can undo the oscillation. And this would be the power spectrum of initial fluctuations. Okay? How much tohu was dropped in the long wavelengths, how much tohu was dropped in the short wavelengths, or more precisely, how much tohu was dropped early on versus how much tohu was dropped later on. Any inflation might do this. Might do that, So let's see. Let's parameterize this by a power law. The amplitude of waves will be proportional to L to ns minus 1. Remember, L is 1 over wavelength. If ns was 1, this would be exactly constant, right? So this would be so-called scaling variant. Variance is independent of scales. Inflation predicts ns is less than 1. And finding ns less than 1 has been the dream of cosmologists over the last 40 years. So Kobe, for example, 1994, they provided the first hint that ns is consistent with 1. But Kobe didn't have really a telescope, so they could only measure very, very large angular scale fluctuations, only very coarse-grained view of the universe. In terms of L, it's 3 to 30. WMAP measured things up to L of 1500. And we were able to say NS is less than 1, but only slightly more than 2 sigma. So we wouldn't certainly claim a discovery using WMAP alone. Now you see that in order to measure NS, so that's the tilt of this thing, it's better to cover wide range of wavelengths. But with WMAP, because WMAP's antenna is only 1.5 meter, you can't really fly 10-meter dish to space. It's too big to fit into the rocket. But you can build large telescopes on the ground. So for example, you can build a 10-meter telescope in South Pole, or you can build a 6-meter telescope in Chile. So this is led by Princeton University. This is led by the University of Chicago. Then with this, you can measure shorter wavelengths fluctuations much better. And with this longer lever arm, we can determine NS better. Now we have 3.5 sigma hint for NS less than 1. And for most cosmologists, 3.5 sigma will be sufficient to convince that NS is less than 1. But to really prove that we all came from quantum mechanical fluctuations in the early universe. So it's such a remarkable thing to say. It's better to have more significance. And to do this, we combined cosmic micro background results with the distribution of galaxies, and we got NS less than 1 for 5 sigma for the first time in 2012. So 2012, December, we posted the paper to the archive claiming the discovery of NS less than 1 at 5 sigma. But then, there was some worry that, because that's a grand claim to make, it would be better not to combine CMB data and galaxies. It would be not much nicer to say this using only the cosmic microwave background radiation data. This happened a few months later. So WMAP was a NASA mission. Planck is ESA mission, European Space Agency mission. And then a few months later, they posted a paper to the archive. I had this anxious moment, right? What do they find? And they finally show using combining WMAP and Planck. So only using cosmic micro background data alone, they confirmed that NS is less than 1 at more than 5 sigma. That was the monumental period for cosmology. Inflation prediction is confirmed. It's a strong evidence that everything we see in the universe, galaxies, stars, planets, eventually life on Earth, life anywhere in the universe, came from quantum mechanical fluctuation in the early universe. And there's another line of evidence. So we measured the power spectrum. That's the like a variance, right? It's a variance of the probability density function. This is the probability density function itself. It's a histogram of the number of pixels that have a certain value of temperature anisotropy. It's bell shape, Gaussian. And quantum mechanical fluctuations predict that the wave function of fluctuation should be a Gaussian if it's coming from the vacuum ground state fluctuation. Do we see this in the WMAP data? So this is a prediction, and that's the data. So black histogram is the data. It's a beautiful confirmation of the Gaussianity. So it looks like inflation driven by single field, like a scalar field, single energy component, predicts NS is less than 1. Fluctuations are Gaussian. And I didn't have time to talk about this, but fluctuations are adiabatic. And there must have been super horizon fluctuations. This very large stretching of the fluctuations to macroscopic scales. All of these are now confirmed. Are we ready to say that inflation happened? I think yes. But to completely convince the entire community, not just a handful of cosmologists, we want more. And that's the gravitational wave. Now, why do we need more evidence? We could just stop here. We achieved so much. Why can't we just be happy and then, do something else? Well, Carl Sagan nicely put it, extraordinary claim requires extraordinary evidence. In saying that there was a period of inflation, making size of atomic nucleus to the size of solar system in a fraction of a second, we all came from quantum fluctuations. It's better to have even more evidence. Yeah. So everything I told you so far is like the quest so far, the quest we had so far. Now I'm going to tell you the new quest. So gravitational waves are coming towards you. Gravitational waves are ripples in space-time, and you can't really see it by your eyes, but it's easy to visualize it. You just sprinkle point particles, test particles in space and watch how they move. And when they move like that, it means that the gravitational waves are coming from the back of the screen toward you. Or gravitational waves are coming from behind you and toward the screen. Okay, either way, it doesn't really matter. And there are two polarization modes, plus and cross, which I will explain later. So I put X and Y axis here. And then so this is the anisotropic change in the distance between 2 points. So easiest way to define gravitational wave would be to just define distance between 2 points. In Cartesian coordinate, distance between 2 points will be dx squared plus dy squared plus dz squared. And let's not forget that the universe expands, so you put scale factor in there. So this will be isotropically expanding space, distance between 2 points. So far, no distortion in space yet. Then let me write this dx squared plus dy squared plus dz squared in a slightly fancier way using Kroneker's delta. So you have delta ij, that's 1 for I equals j, 0 otherwise, and you can put in this form. So far still, the space is undistorted. Now you put distortion, Hij. 3 by 3 symmetric matrix, 6 elements, distortion in space. But now we require some conditions on this 3 by 3 matrix. First of all, gravitational waves are like electromagnetic waves. Distortion in space should be perpendicular to the propagation direction. So this requires, right, let's say propagation direction is k vector. K vector dot product Hij must be 0. So this gives you 3 conditions for Hij. Another thing is gravitational waves do not disturb density. This does not create density waves. So then this requires that this distortion in space conserves area or does not change determinant. Therefore, this part has to give you determinant of 1. And this means Hij is traceless. This is one condition. 6 minus 4 is 2 degrees of freedom. And we can call this plus and cross mouse in this particular coordinate system where gravitational waves are propagating in the z-axis. Okay? That's what we are after. So you have 2 polarization modes, plus and cross modes, and let's see what they do. How do we detect them? So how do we detect them, right? A typical way, well, the most famous way perhaps, because it has been already done this way by LIGO and Virgo collaborations, you have 2 mirrors, you have beam splitter, you shoot the laser from the left, you beam split, one laser goes to the above, another laser goes through and hits this mirror, and they're bounced back, recombined, and then sent to the detector. Now, initial configuration is such that these laser lights are shifted by phase, so crests and troughs of laser light would cancel if there was no distortion in distances to mirrors. But when gravitational waves propagate, they change distance between 2 points. So mirror is slightly pushed away. Well, here mirror is slightly squashed. Distance between mirrors will change, and crests and troughs no longer cancel, and you see the signal. That's how you detect gravitational wave by laser interferometers. But the wavelengths of gravitational wave you can detect by this method is the size of the Earth. If you have detectors on Earth, if you fly a detector in space, maybe you can get million kilometers bigger than size of the Earth. But the size of the wavelengths of the gravitational waves produced during inflation is something like billions of light years. So how do we see that? I mean, you can't use this method to measure wavelengths of billions of light years. Then you use cosmic micro background as a detector. You have an isotropic radiation field, that's cosmic micro background, and then gravitational waves are propagating through it. When gravitational waves stretch space, they also stretch the wavelength of photons, cosmic micro background. Longer wavelengths is lower energy, so it's colder. Yeah, there's a colder photon here, colder hot photons here. Then you put electrons, and this electron will see hotter photons coming from the above, hotter hot photons coming from the bottom, colder coming from the side. And when this light was scattered by electron, right, you see hot photons coming from the above, go to electron, scattered and coming toward you. Colder photon coming to the electron, scattered and coming toward you. These lights are polarized. Why? Well, we have some daily example here. When sunlight is coming from the above, gets scattered by the windshield of the car and coming toward you. This photon is horizontally polarized because if you actually use polarized sunglasses that would transmit only the vertically polarized light and block horizontally polarized light, you can actually see through the car. Okay, Talex is the company that makes polarized sunglasses, and they kindly gave me these nice photos. Well, more precisely, okay, so what's the necessary and sufficient condition for generating polarization? You need to have anisotropic incident light and scattering. For this case, you have preferred direction of the incident light. That's the sun direction. And you have a scattering or reflection. It's the same thing. Of course, the universe is isotropic. So for the first moment, you would think that it shouldn't be any polarization because the universe has no preferred direction. For example, if there's a photon only coming from the left, then indeed scattering will produce polarized light because it scatters only one direction of polarization here. But universe is isotropic, so when the light is coming from everywhere with same strength, the net result is no polarization in outgoing photons. But when you have hot, cold, quadrupole temperature anisotropy around an electron, just like what you saw previously in the gravitational wave example, you produce polarization. Okay? So universe doesn't have a preferred direction, but electron can see locally anisotropic radiation pattern. Okay, so here's temperature anisotropy. You put now the lines representing direction of polarization and size of the polarization, you get this. So this is the polarization measured by Planck observations over the full sky. Analyzing this is slightly tricky because polarization has directions. So what we typically do is to decompose these patterns based upon the parity, how they look in the mirror. Precise way, you go to Fourier space, you look at direction of the wave, L. So now L has a vector. It's a vector, no longer the scalar. It's a direction of Fourier mode. And you look at modes that have polarization directions either parallel to or perpendicular to the direction of wave number. That's called E mode. B mode is a 45 degrees tilted version of it, right? So then you look back here. Then see, for example, you have blue, red, blue, red, blue, red. That's a wavelength, right? That's the propagation direction of the Fourier mode here. Then you look at how it's either perpendicular to parallel to the wave number or not. So that's how you do the analysis. Okay. And indeed, if you flip the space coordinate, so parity flip, E mode remains the same, but B mode changes the sign. So B mode is parity odd, E mode is parity even. Then you take the amplitude of this, so you square E coefficients, both are parity even, so it doesn't change under parity. B, although B itself changes sign under parity inversion, product doesn't change the sign. So it's parity even also. Similarly, temperature polarization cross correlation, E mode, doesn't change sign under parity. So these are all parity even. They exist in a parity even universe, parity conserving universe. Other combinations such as TB and EB are not invariant under parity flip. So they should be zero in a parity conserving universe, but they are non-zero in parity violating universe. So you can actually use these to probe the parity violating physics in universe. That's not the subject of today's lecture. So let me just stick to parity conserving combinations, but remember that these are very, very interesting things. Okay, then that's the power spectrum. So this is the temperature anisotropy power spectrum you saw already from the WMAP. These are E mode power spectrum measured by both Planck over the full sky and then ground-based SPT, South Pole Telescope in South Pole. These are also coming from sound waves. And you see B mode polarization coming from gravitational lensing of E mode sound waves. So all of these are coming from the density fluctuation. And what's missing so far is a B mode polarization from the gravitational wave. This is the only thing that's left undiscovered in the cosmic micro background as a prediction of the inflation, right? We discovered everything else. Only if this thing is missing, and we really want to find this. So how do we find this? Currently, there are many ground-based and also balloon-based experiments are going on. So you already heard about Atacama Cosmology Telescope in Chile, led by Princeton, South Pole Telescope in South Pole. But then you have CLASS Telescope in Chile, led by Johns Hopkins University, Bicycle Array, led by Caltech, Harvard, Minnesota, and then Stanford, and then Simon's Array, led by UC Berkeley, San Diego, and then Japan. So these are, many of them are, most of them are actually led by US. And each of the experiments is about 10 million US dollars. They're ongoing, and we shouldn't be surprised that any of these experiments will announce the discovery of gravitational waves anytime soon. They're taking data as we speak. But now, at the same time, CMB scientists realize that maybe $10 million isn't very enough to really make discovery like what we are after. So maybe we should combine the forces and then make $100 million experiment called Simon's Observatory. If that's not enough, maybe we make $600 million experiment called CMB Stage 4. So this will be late 2020s. So we hope that the machine like this one would allow us to detect gravitational wave from inflation in the form of B mode polarization. I'm involved in this CCAP telescope mission. So we're hoping to start taking data next year. So let's see what that brings us. But if that's not enough, we go to space. But before I say that, let me tell you something remarkable here, okay? So let me actually go back to here. And this is something I wanted to really say to young people. It was 1970 that Jim Peebles, his student, you, and then Vashisnev and Yakov Zerdovich predicted that there will be sound waves. None of them thought that this will ever be detectable, ever, okay? It was discovered in 1999 and 2000, so 30 years later. And this is today, okay? So only 20 years between here and there. There's a 7 order of magnitude improvement in sensitivity here. 7 orders of magnitude, okay? That's just remarkable. And this tells you that just don't be afraid of discovering or calculating something that seems too small to be observable. If it's important, if physics is beautiful, if it's worth measuring, we'll get there much, much faster than you might think. So really the mission of the scientist, don't be constrained by money. Don't be constrained by what we can perhaps do today. Just stick to the physics principles. If it's in principle detectable, it is detectable. Look at the gravitational wave. I mean, how many years have passed since the original concept of the laser interferometer? It's a similar story. And when was it that Einstein predicted it, right? It's more than 100 years ago. So cosmic micro background research is lucky in that sense. It's only 30 years, right? So gravitational wave is 100 years. Just don't be afraid. And also the message to the senior scientist, when you hear brave young scientists talking about something that seems really tiny in the conferences, don't discourage them. I mean, okay, sure. We may not see the discovery of such tiny effects within our scientific life, you know, but they have more years before they retire. So remember that, you know, just encourage them, don't discourage. Not, you know, simply because effects are small. It doesn't mean that they will never be observed. It just has to be interesting, that's all. And there are lots of interesting things going on. Now, but this improvement didn't come for free. Experimentalists have to work very hard to improve the noise level of the experiment. And there's a Moore's law here. It's an exponential improvement in noise level over the years. It's remarkable. And essentially, WMAP had 10 detectors. And then now CMBS4 is planning to have 500,000 detectors. This is amazing because this many detector is not needed for anything else except CMB. You don't need so many microwave sensors for any daily life applications. You just don't need it. but because people thought that this is important for CMB, you know, people became very clever about creating superconducting detectors. WMAP used traditional radiometers, like a technology used by radios. Planck used semiconductor detectors. Now we're talking about using 500,000 superconducting detectors, right, cooled to very cold temperature, like 0.1 Kelvin, 100 microkelvin. Something just industrial scale, and it's remarkable that science gets us so far in technology as well. If that's not enough, we go to space again. And I'm very pleased to let you know that Lightbird, this will be the 4th generation CMB dedicated satellite. So first COBE, then WMAP, then Planck, and Lightbird. And this is led by JAXA. This is the first CMB experiment led by Japan. But we need partners, so we partner with NASA, Canadian Space Agency, and European Space Agency, and member states to fly this thing. We have few thousand superconducting microwave sensors in space, and we go to L2. So let's see. So let me summarize. New quest. Quest so far. The inflation driven by single energy components such as scalar field looks very good. We have a lot of evidence in support of that. And as less than 1 milestone in 2012, 2013, Gaussianity, adiabaticity, and super horizon fluctuations, all of which are beautifully confirmed by experiments so far. None contradicts with inflationary prediction. The new quest, the only thing that's left discovered as a consequence of the inflation is B-mode polarization from the primordial gravitational waves. And I hope that the ground-based and balloon-bound experiments will detect this within the next 10 years. If not, we'll find it in, if they find it, we have definitive measurement of the power spectrum and Gaussianity using Lightbird and CMBS4 in early 2030s. I really hope that will be the thing, right? We detect this first in next 10 years, then have a definitive measurement by more sensitive experiments. If we couldn't find it, we'll try to find it using Lightbird and CMBS4. We'll see. I stop here. Thank you very much.
Wow, thank you very much, Professor Komatsu. I think it's been a really brilliant lecture, and I bet a bunch of us would probably go to the kitchen and start doing physics experiments as dropping tofu of different sizes.
Yes.
And you know, and I'm putting myself as the in between of the ages of scientists. So, you know, I try not to be afraid, not to be discouraged, and at the same time, I try not to discourage other people, young people.
Right. Yeah.
Thank you very much. You've got lots of interesting questions awaiting you. So if I may read some of them, a number of them would probably ask you to just explain a bit more about inflation. So what is cosmic inflation and what causes inflation?
Yeah. So definition of cosmic inflation is the exponential expansion. There's no other definition, basically. So let me here. So it's defined to be the exponential expansion of the universe. The question is, what caused it? And the simple answer is, we don't really know. So essentially, it's the same as dark energy that making universe exponentially expand today. It's just that you might have also happened in a very, very early universe, not just today. Okay. And the simplest model of inflation utilizes one energy component that has funny equation of state to make the universe expand with acceleration. So this would be so-called a scalar field, similar to Higgs field, but the shape of the potential of the Higgs is something specific. Shape of the inflationary scalar field potential would be something completely different. So we think it cannot be Higgs field in the standard model, but with some modification, we can make inflation work. But you shouldn't be really constrained by that. The most correct answer, what drove inflation, we just don't know. So we just find out by making more detailed measurement of the power spectrum and also detecting gravitational wave.
Thank you. Well, the next question is still on inflation. Is the field of inflation coupled to the rest of the fields known as the standard model? Would primordial gravitational waves be measurable with our current instruments? Well, you've indicated some part of that. So would you like to?
Yeah. Yes. So yes, first question, is inflation coupled to the rest of the world? It could, but it doesn't have to. So, but it has to couple to something, okay? If inflation is not coupled to anything else, inflation ends, inflation just dilutes away, but nothing else happens. Somehow inflation needs to excite other particle species so that universe, after inflation, because inflation is an exponential expansion, everything dilutes so quickly, universe becomes very cold. So after the inflation, universe needs to be repopulated by particles and must become hot. Otherwise, we can't produce helium and light nuclei. Yeah. So how did that happen? It's called the reheating process. And once again, I'm sorry to say, we don't really know how that happened. But the basic idea is inflaton is coupled to some species. Doesn't have to be all standard models, but something. That something is then quickly populated and then re-thermalize the universe. Then the rest of the particles will be thermally produced. So that's the simplest way. But there are other mechanisms. For example, you could actually couple inflaton directly to some of the standard model particles. The easiest one would be neutrinos, for example, because we don't understand so much about neutrinos. You can couple to neutrinos, neutrinos then couple to the rest of the world, and then the universe becomes hot. I must also say that, however, there's another way. So inflaton, even if it's not directly coupled to the rest of the world, of course, inflaton must be coupled to everything else by gravity. Now, usually gravitational force is too weak to enable thermalization of the universe. But if the gravity theory was not Einstein's gravity in the early universe, but somewhat modified gravity, then gravitational strengths could be different in the early universe, in which case you can have the just enough strength of the interaction between inflaton and the rest of the world gravitationally to reheat the universe. So this is also possible. Second question, how can we see gravitational wave from inflation? So quantum mechanical fluctuations produce fluctuations, both density and gravitational wave at all wavelengths. Therefore, we can see this in the cosmic micro background, whose wavelength is billions of light years. But also we can use laser interferometer to see gravitational wave from inflation wavelengths of 1,000 kilometers. We can also use pulsar timing arrays to detect gravitational waves in the intermediate wavelengths. So there are multiple ways to measure gravitational waves from inflation, but so far CMB has the best chance. But once it's found by CMB, then we should also look for signatures in other experiments.
Great, thank you very much. Well, the next question has to do with your previous answer, because it mentions about quantum fluctuation. Do we have any proper evidence of quantum fluctuations in the early universe? If any, can you please briefly explain it? So
yeah, so the first evidence is NS. So this NS less than 1, okay? This thing here, right? So this rather than that is an evidence for quantum mechanical fluctuation, because it's built on Heisenberg's uncertainty principle. The amount of fluctuation you can get is proportional to expansion rate, h. That's a dot over a. H is a decreasing function during inflation for fundamental reason. So h has to decrease. This means, so this is now, essentially what you're seeing here is the h as a function of time. This part is later during inflation. This part is earlier during inflation. So h has to decrease, right? But to enable exponential expansion, NS cannot be so much different from 1. H has to be roughly constant. So it's a very subtle thing. First thing you want to show is NS is consistent is 1. But second thing we want is that NS is less than 1. NS consistent is 1 was discovered in 1994. But it took us many more years to discover NS less than 1, finally, with 5 sigma. That's the strongest evidence. The second strongest evidence is the distribution function of temperature fluctuations. If it's quantum mechanical fluctuations from the vacuum, ground state, fluctuation should be very close to Gaussian distribution, normal distribution. And we see it. So that's the second strongest evidence. And with these two, we hope that we have a very strong evidence for quantum mechanical fluctuations in the early universe. This doesn't, however, mean that the gravitational waves are quantum mechanical fluctuation, and it could be, but we should test. We should also test whether it's scale invariant, no? NS equivalent of gravitational wave is consistent with scale invariant, and also Gaussian, right? We have to show that the gravitational waves are also Gaussian before we say it's quantum mechanical.
thank you very much. And perhaps the role of inflation to sort of make the fluctuation at quantum realm into finite size, right? To be processed later on. Yeah. Okay, the next question is, I know that inflation is so successful and provide explanation for many phenomena, but some experts such as Steinhardt give it up and move towards cyclic models. Can you comment on that, please?
Yes. So it's very healthy that there are always alternatives to standard paradigm. And we just have to ask the universe, right? We can't base our judgment on our only theorized ideas. We have to just, whenever we're stuck, don't know which one to choose, we just have to ask the nature to give us an answer, right? That's that's a deciding factor, nothing else. So Professor Steinhardt and his colleagues tell us that this equiprotic universe doesn't have H that's roughly constant. So H is not close to constant during inflation, during the egg process or cyclic universe. Therefore, they do not predict the detectable gravitational wave in CMB experiments. In other words, if CMB experiments discover B-mode polarization from gravitational wave, they will say, they would also agree that it's not egg process, it's inflation. So this actually goes back to this question here. So did inflation happen? We have very strong evidence for it. But why more evidence is needed? Because extraordinary claim requires extraordinary evidence, and there are alternative ideas to inflation. Deciding factor will be then primordial gravitational wave. And with this, we hope that we can settle the argument. Now, what if we don't discover gravitational wave? Well, then I will think about it at that time, but not now. Okay, we're very busy trying to measure this thing. So.
Okay, certain things, require us to wait, and there are the things that we need to worry about. Okay, there is a question that regarding the NS. You showed that we can get NS less than 1 with very low sigma by combining results from CMB and galaxy distribution. But then you mentioned that more cosmologists would be more convinced if we can show it using CMB only. Why is that so? Isn't it better to have different sources confirming the same thing?
So the last comment, isn't it better to have confirmation from everywhere? I completely agree. Yeah. So basically, I think you gave answer yourself. It's good to have confirmation everywhere. For example, if this CMB only result came first, I would also say the same thing, but wouldn't it be also good to confirm it by combining different data sets? So that's all. You just said the right thing. Just good to confirm by independent experiments. That's all. That's all I wanted to say.
Great, thank you. There's another question regarding quantum fluctuation. In the time of inflation and quark era, quantum fluctuation created particle and anti-particle pairs, and they annihilate each other. Then how some particles remain and not get destroyed?
Right, so that way of thinking about a quantum mechanical fluctuation may be popularized by Stephen Hawking for Hawking radiation, and some of the inflationary scientists say the same thing in public lecture. That analogy is not correct. We don't have that kind of picture where particles, antiparticles created, one goes the other, whatever. That's just wrong. So that's not how it works. And so please forget it. but I myself have said it before in public lecture. I completely regret about that because it's so difficult to explain. And public is really, unforgiving. they really want to know. And but I can't possibly use equations to explain it. And it's a challenge. And that's why we need the science communicators to do outreach on our behalf. And actually, let me tell you something. So people often ask, let's see, I think people ask you too, but let me say, so I'm Japanese, I live in the US and I'm in Germany, and people sometimes ask me, what language do I think? Japanese or English or German? And then my answer is math, it's mathematics. And but then when I try to explain something to people, I translate math into language. But then there's something lost in translation, right? Because we can't possibly use math for general public. And when people get confused by our explanations, we can't really blame them because we're not explaining well. We're not translating it well. And this antiparticle particle stuff is one of them. Another, actually, famous example is probability quantum mechanics and general relativity. We don't question the validity of these things, but of course, public always questions why. It's not because they're stupid, they're very smart. It's because we are not able to translate into language yet. And it's our fault. So yeah, I always think about it and I still haven't found a better way to explain quantum fluctuation. I mean, what I said today is best I could come up with. And I didn't use particle antiparticle analogy because that's incorrect.
Yeah, I can relate to the challenge of having to explain, especially the physics of the early universe. You know, even we don't really understand the physics.
That's
I mean,
right.
there are lots of things going on which are, you know, entirely different from what we are experiencing
Yeah.
in the other parts of cosmology.
Yeah. And so
Yeah.
one thing I learned by giving public lectures is public loves when we say we don't know. So if the answer is we don't know, say it. That's the best answer.
Yeah.
And they're willing to pay tax to support our science. You know, they like our science and they love it when we don't know. So they're willing to support more. So yeah.
Well, there are more questions if you don't mind. Okay. Is there any possibility to find any other way to describe inflation other than single fluid slow roll inflation?
Yes. So very interesting model has been proposed recently. So scatter field, we know it exists, it's Higgs, right? But it's not so much more. On the other hand, there are gauge fields, which are much more ubiquitous. You know, you have electromagnetic fields, you have weak field, you have strong field, right? U1, SU2, SU3 gauge fields. These gauge fields can couple to scalar field, and they can aid inflation. So even if potential of inflaton is too steep, so therefore it's not single field slow roll inflation, coupling to gauge fields produces lots of gauge fields, and inflaton field loses kinetic energy by that coupling. So this so-called gauge inflation, so gauge inflation and other versions of it is a good example. Reason why it's good example is that, okay, so not only it is not single field slow roll inflation, but also these gauge fields can directly produce gravitational waves, not by means of the quantum mechanical fluctuation in the vacuum. It's not the vacuum. It's actually gravitational waves sourced by gauge fields. So that's, I think, the very nice example. We've written several papers about it. This was pioneered by brilliant Iranian physicist Azadeh Maleknejad. She proposed this in 2011 when she was a graduate student in Iran. And then, you know, so I recruited her because the work is so brilliant. And she spent postdocs in my institute for 3 years until the end of August. So it's like a few weeks ago, and she is now a postdoc in CERN. So if you're interested in this class of models, gauge inflation, just Google Azadeh Maleknejad. It's a great thing. So this model is distinct because it predicts that gravitational waves are not scalar invariant and gravitational waves are highly non-Gaussian. And gravitational waves are parity violating because gauge fields can break parity, like weak field, and then this can produce these TB and EB correlations. So, so yes, there are plenty of examples of non-single field, non-slow roll inflation, and this is one of the interesting models.
Thank you. More question on gravitational wave. So how will primordial gravitational wave of inflation differ from stochastic gravitational background resulting from astrophysical processes in the more recent universe?
Yes. So it differs in one very significant manner. The wavelength is very, very long, right? So it's the frequency of gravitational wave that we're trying to detect by CMB is 10 to the minus 18 hertz. In terms of the wavelengths, it's billions of light years. On the other hand, all the other stochastic gravitational waves have wavelengths of, you know, astrophysical wavelengths, not billions of light years. 1,000 kilometers, million kilometers, but not much more than that. That's very distinct. That's why CMB is such a powerful thing, because it cannot be astrophysical.
Well, this one is interesting. in the near future, if B-mode gravitational wave is detected and inflation is confirmed, what is there remaining for us to do as cosmologists?
So inflation is confirmed, but what drove inflation, right?
Right.
We go back to, so look at dark matter. Dark matter exists, but it didn't stop us because we don't know what dark matter is. And the cosmic acceleration today is confirmed by multiple experiments. We didn't stop. We don't know what caused dark energy. It's same thing. Once we confirm inflation, we have to know what drove inflation. And that's the next thing. And of course, the most important question is what happened before inflation, right? If you speak to kids, right, they are like, where am I from? And you say, you're from me, the mother. You came from my belly, and then they ask us, where are you from? And I say, I came from your grandmother and the grandmother, and eventually we say, we came from ocean, and then we came from Earth. And we say we came from the protoplanetary disk. And we say we came from the Milky Way. Then we say, actually Milky Way came from quantum mechanical fluctuation. Then they still ask, where does the quantum mechanical fluctuation come from? And they say, go to bed. It's none of your business. Or you go to university and study and then see it yourself. But they're not satisfied. So okay, there might be some inflation. And then they ask us, what made inflation? Well, it was before inflation. They never stop. And we are doing the same thing. Just keep asking the questions like kids. And it's never ending. Very exciting.
Great. So infinite regression there.
Yeah.
So, you asked about initial condition. That's a huge question. People probably try to sweep under the rug and creating multiverse ideas and stuff.
Yeah.
So here's another question, which is slightly different from others. Is 5% baryonic matter model the only solution for the simulation to match the observed power spectrum? Are there other possibilities or more of fewer ingredients in the soup?
Right. So I think we are convinced that we need at least 3 ingredients: baryons, dark matter, and dark energy. Now, let me be actually more precise. It's impossible to fit a power spectrum with fewer degrees of freedom than 6. So you need 6 things to explain everything. 5 doesn't work. 4 certainly doesn't work. So what that is 6? It's the NS, actually. So if NS were 1, we would only be happy with 5 parameters. But NS is the one, so you need 1. Then you need amplitude of initial fluctuation, that's 2. Then you need so-called optical depths of fluctuation. Some of the photons coming from last scattering surface were rescattered by free electrons in the today's universe, that's 3. But the rest would be baryon density, dark matter density, and dark energy density. Now, so you need at least these 6. It doesn't work other way. Now, why do we say baryons in dark matter and dark energy? Actually, what we really do here is baryons are just name for matter that interacts with photons, okay? Electrons. Now, protons and neutrons don't really interact with photons. They do, but much lesser degree. But the protons interact with electrons by Coulomb interaction. And electrons and photons interact by Thomson scattering. So indirectly, protons and photons are tightly coupled. Neutrons, they form helium nuclei. And helium also has the 2 protons, right? So they interact with electrons, the electrons interact with photons. So all these, ordinary atoms that we know interact with photons. So that's one ingredient we must have. The other ingredient is gravitational potential, right? And then what we found was that gravitational potential is actually deeper than what's possible by ordinary atoms. That's why we need dark matter. Yeah. So dark matter is really different way of saying deeper potential. And dark energy, so now you add up baryon density you measure, dark matter density you measure. And this is all matter, there's nothing else. And you try to calculate the present day energy density of this stuff. You can do that unambiguously. Then, because they dilute by volume as the universe expands, we know precisely how that works. Then you compare that to the total energy density in the universe, and it doesn't match. So we have something that's not matter that makes up the rest of the universe. So that's dark energy, right? That's how we kind of coined the name, because that's not matter. That's all, right? So when we say baryons, dark matter, dark energy, we don't really mean what the names are, but just that we mean by matter that interacts with photons, matter does not interact with photons, and the rest. That's probably a more precise definition of what these three ingredients are. And yes, we're convinced that we need at least these 6 to fit CL. Fewer degrees of freedom just wouldn't work. More degrees of freedom certainly work. You can start adding a lot more, but fewer doesn't work.
Wow, that's definitely an insight for all these participants who have been trying to cram everything about dark matter in a fortnight. So, well, there's a question regarding the Gaussian distribution. So, does the width of the Gaussian fit with the prediction? And would you just elucidate a little bit more about non-Gaussianity presence in the idea?
Sure. Yes. So before you look at PDF, probability density function, you can always compute variance. In fact, power spectrum is basically variance, right? So we know the variance, we measure it. Then, yes, there's no free parameter here left. You just plot the Gaussian distribution with that variance, and it fits. But in practice, we do a lot more. So this is the simplest thing you can do. More elaborate thing you can do is to use so-called 3-point function. So this power spectrum is a 2-point function. It's the squared amplitude of temperature, right? You have one temperature, multiply that by one temperature, and the average. That's what you're seeing here. 3-point function is now you have temperature in one direction, temperature another direction, temperature third direction, and average over the sky. This is more than 1 point PDF because this is temperature in one location, temperature in the same direction, and temperature in yet same direction. All temperature, same direction, cubed, averaged. This is PDF, 1 point PDF. So we can do this 3-point function to do much more precise test of Gaussianity. And by doing that, we find using WMAP, deviation from Gaussianity in WMAP data is at the most 0.2%. With Planck, we improved it to 0.03%. So there may be deviation from Gaussianity, but cannot be more than 0.03%. And that's pretty Gaussian. You know? I certainly haven't seen anything more Gaussian than that in my life, except noise. Noise is very Gaussian, but Gaussianity at this level is quite remarkable.
Yeah. Okay, I think we've got 1 more minute for your question and answer session. Let me just end this with a question that has to do with the expansion of the universe during the inflation. The inflation is, exponential expansion, so it expands with the speed higher than the speed of light. How could that not conflict with special relativity. And yeah, I think it's there's some misunderstanding about special relativities, the limit of speed of light, and the expansion of space itself.
That's right. Yeah. So yeah, exactly. So yes, expansion of space completely contradicts, but special relativity assumes static space-time. To study the dynamics of space itself, you just can't use special relativity. That's all. So you need general relativity, and general relativity does not prohibit expansion of space at any rate.
Okay, the next one is probably more philosophical or pedagogical. The scale of loss in translation that you mentioned for the public lecture is increasing with time as physics and maths are getting more complicated. What do you think would be the solution to this?
I think we have to work more with science communicator.
Mm-hmm.
Just give up on doing it yourself. Just get help with science communicators. They are very educated and they know how to talk to general public, right? I mean, challenge is really, we don't really know what public wants to know. What makes it easy for them to understand? We're completely decoupled, right? The explanation that we find easy is not necessarily what's easy for them. But science communicators know, what to say. That's really incredible. But they themselves have to be kept updated on the latest development. So what I find very useful, effective is to just talk to scientists talking to communicator directly, and then let them talk to the public. I think this is very useful. And that venue can be also simpler. No? If you wanted to have talk in a museum, you're in front of a few hundred general public, that's too much. But if you just speak to 20 science communicators, even 10, that can be done at a much deeper level and quite effective. So that would be one solution, I think. Yeah, creating movies like what I showed, more and more. And but if you let public make such movies, they're all wrong, right? So that's bad also. So we have to be behind the scene. Have to work more closely with science communicators.
Right, it's very complicated, but it's our duty to make sure that bad science doesn't creep into bad movies and
yeah, that's right.
So thank you very much. We're pretty much the end of our lecture. Thank you very much, Professor Komatsu.
My pleasure.
And we've got this nice tradition of having a group picture. So everybody, please turn on your video for us so we could see you and Professor Komatsu could see you as well. And we can take pictures. Right, so you can just okay, and then at the same time, if you all could join me in giving the warmest applause that you could give to Professor Komatsu. It's been a hugely great lecture.
Thank you, Professor Komatsu.
Thank you,
Thank you very much.
Thank you.
Okay, we're ready for picture.
Thank you.
I'll just keep talking while
Saya nggak bisa
waiting for
buka
the
itu
photographer.
kamera.
Ready?
Saya nggak bisa.
Jadi ditutup oleh host, Bu. Video saya di blok oleh host.
Let's see.
Ya, sudah bisa.
Could you allow Ilham to take picture, please? Or somebody?
Techniques, please.
The participants coming from 18 countries, Professor Komatsu. So
nice.
You're speaking to the whole world.
Yeah, very nice.
Are we ready, photographer?
Okay, I will help you to take a picture. So
excellent, thank you, Anton.
Okay, okay, be ready, everyone.
Try to look happy, everybody.
Come on,
okay,
smile.
first slide. Okay, I have 3 slides here. Slides. Okay, first one. And second one. Wait a minute. Okay, the third one. Wait a minute.
Hold your smile. I can't tell which layer this is now. So.
Okay, done. Okay, thanks everyone.
Thank you, everybody.
Thank you, Professor Komatsu.
Thank you very much.
Thank you.
Thank you, Professor.
Thank you, Brana. Thank you, Pak.
Thank you.
We are stepping on to the next part of this.
Brana. Thank you, Pak.
Thank you. The summer school is going to end very, very shortly. So I will hand the chair to Anton, who will lead the closing ceremony, if you will.
Okay.
So everybody, please stay and enjoy your cookie and coffee.
Okay, thanks, Dr. Premana or Premana-san, since our guests now come from Japan. Okay, and also thanks for Komatsu-san. So your lecture is very insightful as usual. Yeah, you give us a great lecture. So thank you very much. And now, before I give you my closing remarks, so maybe I will give you a little bit gift. Maybe I can. So this one, since our summer school is about dark matter, so if you like rap music, so you can hear this music.
No Skills Entertainment. Space stuff. Dark matter.
Look up in the sky, there's the moon you see. There's some stars, there goes Mars, Pluto, RIP. Those are just a few of the things in our galaxy. All of it's held together by tons of gravity. But what if gravity wasn't strong enough? Everything in the universe is held by some other stuff. Some other stuff you cannot see with the naked eye. Some other stuff that doesn't shine when it's hit with light. It seems that we have ourselves another mystery. So let's travel back in time to 1933. Fritz Zwicky was observing the coma clusters, and this would lead to an astronomy adjuster. He was measuring those galaxies' mass, and based on the observed mass, they were moving way too fast. There had to be something else to cause such speeds. Apparently, we have...
Okay, sorry, I need to end here because maybe there is some copyright, but you can continue.
Thank you.
If you enjoy this music, you can go to YouTube and try to listen by yourself. Okay, now, okay, I will start my closing remarks. So, okay, yeah, as you know that we are all facing the global pandemic, so we cannot avoid such a huge impact in our daily life activities, including in science education. So most of us are work from home from the first time as the world tackles this current situation. We need to switch our work mode from face-to-face interactions into the online mode. Of course, it is not an easy task by doing everything online. However, I can say that we can take the benefit from this bad situation. We can break the Great Wall, which is the distance between us, anyone around the world. Now everyone can share, can discuss, learn, and making research collaboration remotely. We know that science is growing faster and stronger with time. We need to maintain the enthusiasm for learning and sharing knowledge, especially in science. We don't want to hear in the future that we have a big gap generation in science due to this pandemic. Yeah, I think this is one of the purposes of this school. Then I can say that I don't know how should I express my gratitude to everyone who has been supporting us during this school. I just wanna say thank you very much for the committee from Astronomy Research Division, especially Galaxy and Cosmology Group. And then the mentors who prepared and helped the participants a lot during the workshops, the technical teams who are always stand by on the back to help us during the class, like the classes, and also Bosca Observatory, Faculty of Mathematics and Natural Sciences, and also our Institute Technology Bandung, Indonesia. So I know it is really exhausted, but you are still do your best for our school. And for all lecturers and also for Komatsu-san here, we have lecturers from around the world, at least from 7 countries. It's our pleasure for having you during this school. Also, thank you for your kindness to sharing with us about your expertise, especially about the universe and about the dark matter. And for all participants from around the world, as Premana-san mentioned it before, come from at least 18 countries. We know that some of you need to wake up earlier than usual and go to bed late to join us. I believe that all of you well done through the 2-week school. It is my great pleasure that you had fruitful discussions through though I think 2 weeks is not enough. Yeah, of course, it is not enough to you learn everything about the universe. But I want to say thank you so much, everyone, for your enthusiasm and also for good atmosphere during lecture and also discussion session. Then on behalf of the committee of the online summer schools on galaxies and cosmology 2020, we apologize for any inconvenience caused and appreciate your understanding. I would like to close my remarks and officially announce the end of the online summer school on galaxies and cosmology 2020. Wishing the bright future for you all. Thank you for your attention. We hope you can maintain our network and let's collaborate in the future. Thank you, everyone, and see you later. Okay. So yeah, okay, thanks everyone. So I will give you